So this is me, I'm Flo. I've been in the software industry for quite a while now. I consider myself quite lucky because I had always the situation that companies gave me money to work on interesting projects and learn new things. It's a thing I really love about this industry. So for the most part, I've been working on e-commerce platforms, data platforms. They've become larger and larger in the last 20 years. And yeah, now I'm here to talk about graph databases. So yeah, working in the industry quite a while, but I decided that today I want this to change and it should be really, really different. So for the time being, I'm going to be your wizard of GraphRAG today. All right, good. I'm being a bit silly here. The reason I'm a wizard right now is that for the example in this show and this presentation, I picked Lord of the Rings as a demo book. So first of all, I thought it probably resonates with some people in the audience here because it's a very popular fantasy book, obviously, but also because it's a very tricky book. There's bazillions of characters and it spawns over decades, and then it's also not chronological in order, but sometimes it jumps back and forth. So for a GraphRAG system which extracts information from that book, it's actually pretty tricky to follow. It's a tough book to do. And this is why I picked it. When I'm not a wizard, I work at a company called eTribes. We are a mix of a consultancy and an agency. So we consult companies and then we build the software that we discussed with them. So it's quite an interesting mix. We are hiring. If you're interested, speak to me after the show. And it's a cool place to work, I can say. So jumping right in. The question that I would like to answer for this sake of the demo today is, what role do Gandalf's absences and returns play in the formation of the Fellowship of the Ring? And how does Bilbo's birthday party fit in? So do we have any Lord of the Rings buff here? Anybody be able to answer this? All right, I couldn't. I'm not such a big fan of it, but this is a complicated question and it's with reasoning. You need to think about this. And also the answer to this thing is spread throughout the whole first book. So it's something that is not just one passage and there it says everything, but this is really all over the place. In case you sort of need to brush up on your Lord of the Rings skills a little bit, this is the correct answer. So Bilbo, who's Frodo's father, celebrates his 111th birthday. Then Bilbo buggers off using the ring, leaves the ring behind. Gandalf sees the ring, gives it to Frodo, the son, goes searching for 17 years. Gandalf returns, confirms it's the correct ring. He then leaves again to consult with his buddy Saruman, who betrays him and imprisons him. During that time, the hobbits take off and meet Gandalf in Rivendell, where they meet the Council of the Elves. This is the correct answer to the story. Any objections to that? So, okay, no big Lord of the Rings ring fans here. And this is what my DIY RAG system made out of that. How I did it is I'm using GPT-5, I'm using Qdrin as a vector database, and I'm using a simple chunking strategy, and I'm taking the first whole book and passing it to the RAG for embedding, and then retrieving it with the LLM. And as you can see, I'm not going to read it out. This is the answer the LLM is giving me, and I think we can all agree it's rubbish, right? It's not really good. One side note I would like to point out, because here it actually tells me that the context does not contain any proper answers to the whole thing. And why it says that? Because I instructed GPT-5 to only use the context I give it and not assume any prior knowledge. So why is that needed? Because GPT-5 has, of course, also read Lord of the Rings, so it's going to be able to answer it. But I want to avoid that because I only want to use the knowledge I pass in via my RAG system. All right, so this is not really good, and let's see if we can make this any better. But before we answer that question, I'd like to sort of go a little bit through the background and the mechanics that are behind GraphRAG. And we're going to do that by starting with how search works. I mean, essentially, if you think about it, RAG, it's retrieval, right? It's been around for 30 years now in computer science, search engines. It's have a huge chunk of data, text mostly, and I want to type in a query, and I want to get the correct result, and this result is what we then use in RAG to give to an LLM, and then it produces the answer. And the simplest form of retrieval, which has been around for, I don't know, also 30 years, I guess, are search databases, so stuff like Elasticsearch. And how they work is that essentially during indexing, you take your book here, you split it by page, by chapter, I mean, it doesn't matter, you can split it somehow, and then you extract all the keywords from those pages. So in this case, we have column and ring, and you remember on which of the pages you saw the keywords here. And if you ever come across the term inverted index, it's quite the thing with the search databases. This is what this is. So you have the keywords, and then there's an index saying, these words appeared on these pages. And then when you query the whole thing, you take this query here, then, okay, a little bit sort of details here that probably the search engine will take the took and turn it into present tense, so take, so it doesn't differ on the times. So basically we have column, take, ring as a search term, and then we look up the index, okay, which pages do these terms occur? And it turns out that column and ring both appear on page 12, so we're going to return page 12 as the first result. Right? Fairly simple, this is this. And this is actually, by the way, also how Lycos and Yahoo and all these sort of first-generation search engines worked. And all Google did was basically tweak that algorithm a little bit, so on how the results are better, so you don't just count the occurrences of a word. There's a couple of problems with this, obviously. The first thing is that this is called lexical matching. So lexical meaning word by word. And if the word differs, because my engine is too stupid to use took and turn it into take and some other sort of changes, then we're going to miss the meaning. So this thing does not match any semantics. So it's just a keyword match, basically. Obviously, you also got the synonyms. So CEO and chief executive officer are going to be two different things. And so it's not going to find it if you search either of them, unless you configure it to do so, but that's quite a bit of work. And then also that if I search for Python invocation, for example, and I'm a software developer, then normally it should be pretty clear that we can sort of take all the snake charmer books and leave them out. But obviously, in this sense, it's not possible because Python is a Python and it's the same word, but it means different things. So it's tricky. It's not so easy to use this. This is now where the vector databases came in since, I don't know, 5 years, 4 years, something like that. And they were completely different, and basically they've been made possible with the advent of all the LLMs. So how they work is that you still take your book, you split it by page, let's say, and then you use an embedding model where you take the page, feed it into the embedding model, and the embedding model gives you a vector. And this vector essentially encapsulates the meaning of that page, the semantic meaning of that. And I can understand that this is a bit wild because a vector, and how does that work? But what I always do is that I think of colors. So if you think about, you have two colors, a reddish color and another reddish color, then these will be expressible as vectors, three-dimensional vectors, or red, green, blue, or yellow, green, magenta, whatever it is. And then you can see, okay, these are two colors that are similar because their vectors are close together, and it's exactly the same with the text embeddings. It's just that the vector space is 1000-dimensional, so it's a very high dimensionality. And in this dimensionality, we have the meaning of the passage encapsulated. Okay, we take that, we store it into a vector database, we have a page, we have shit tons of numbers here, and then when the user comes along, we take his query, we also run it through the same embedding model, also get a big vector, and then we use the user query vector to check which of the page vectors are similar, and then it's going to give us the page that is most similar to what the user asked. Pretty cool. It's awesome technology, really, made possible with LLMs, because the embedding models are also large language models that have been tweaked a bit. All right, there is obviously some shortcomings to this whole approach. So the first thing is the chunking. As we said, we're going to split down the book page by page or paragraph by paragraph. Then the issue you're going to see is that if you're unfortunate and a sentence begins on the bottom of one page and then continues on the next page, we're going to cut off the sentence in between, and we're going to get rubbish because the meaning cannot be encapsulated. So chunking is a problem because it destroys the meaning. Then also the thing is that semantic similarity is not logical connection. So for example, if you take MySQL optimization and Postgres optimization, the vector for these two things will be very close because it's semantically a database optimization. But if I'm searching for MySQL optimization, I'm not interested in the Postgres documents that I have because it's the wrong database. It's not going to help me. So this is a problem, and it's going to give me a lot of noise if I do that. And another thing, of course, where graph models are failing, vector models are failing, is that they cannot do multi-hop reasoning. So if you have complicated questions like the one we had in the beginning with what happens then and what happened that and that and that, they fail at that because they cannot encapsulate this sort of multi-hop reasoning that's behind it. And another thing, and this has actually been biting a lot of people because they think they can ask their vector database, how many orders did we have last month? And you're not going to get a proper answer from that because the vector database cannot count. So it can only give you semantic meaning, and counting is fairly factual. So you have 3 documents, then it's a count 3. This is something where vector databases are out of the game. So it's not going to work. All right, and then there's another thing that I'd quickly like to mention here. It's called the compounding effect. And that means if you have a slight mistake at the beginning of your operations when data retrieval, this mistake will become bigger and bigger and bigger as you go down. So you see here the little problem we have up here. As it slides down, as we progress it more, it's going to get bigger and bigger. In the end, you're going to get rubbish back. So it's sort of a mechanic, and it's been shown that this is actually exponential, the damage it does if you have a small flaw in the beginning. And the thing is, a lot of people think, we just need better embedding models, and then we're going to be good. But no, this is an architectural issue that cannot be fixed with embeddings. This is something that's inherent to this type of architecture. But how can we make it better? And this is what this whole talk is about. We're going to use graph databases or graph systems. Probably a lot of people, I guess everybody here is using graph databases daily. Graph databases are in your car navigation system, for example. The mechanics behind there with your locations and then graphs connecting the roads are the graphs, basically. This is how your car tells you where to go. This is what's behind this, so it's been used for a while. But the usage in this type of information retrieval, this is rather new. Under the hood, a graph database is fairly straightforward. So it's not some magic vector numbers, it's actually quite understandable. So it starts off with that you have nodes, which are things, entities. And to make things a little bit more complicated, you can have different types of nodes, so let's call them meta nodes. In our example here, what I did, for example, I have 2 meta nodes. One is for person and one is for location. And the green ones are just the standard nodes. And I can say Pippin is a person or Woods is a location. So you can have sort of hierarchies within your nodes, so you can express things more fluently, basically. As you also already saw, I guess, between those nodes you have the edges. These are the relationships that exist between the nodes. So you can see, for example, that, let's take this one here. So the black riders may be met on the roads, and the black riders may be met in the fields. So this is the edge between those entities. And then again, this is also rather new. These graph databases allow you to store properties on the edges and on the nodes. So these properties, in our sense, would be the text. So for example, I can have the text on an edge that led to the building of that edge. Or I can store a summary of who that dude is. So all the edges that go in here will be summarized as a text node here on the Frodo node. And also what you can do, you can store vectors here. So you can store a vector on the Frodo node, and then I can search for stuff that is Frodo-like using vector search, as we just saw. So they can do that both. So that's a pretty cool technology here. Why is this good and why is this powerful? So first thing, of course, is that it's way more flexible than a classical relational database. If you have like a table-based database, you need to define your schema beforehand. You need to find, this is has many end-to-end relations. I mean, you know all that stuff, so you need to sort of fix the tables together. With this, you're much more flexible. You can define the entities and the edges basically on the fly, so this makes it powerful. And also there's query languages behind them. Most popular one, I guess, is Cypher. It's the one Neo4j uses. And this allows you to say, okay, go start at this node. So let's take a project work here now. Start on Sarah, follow the edges that have worked on, collect all the projects that she's worked on, and then follow the projects to find the ones that are owned by some other guy. So this is easily possible, quite cool. And obviously this is the same thing that would allow us multi-hop reasoning, because I can now say, Sarah has worked on this project, and this project is depending on another project which is owned by another guy. So this is something that is actually quite tricky to do in SQL if you want to do this, because then you're going to end up joining the same tables over and over again. You're going to have this, I don't know, depends on table, and this will be a lot of joins there, and at some point you lose track on what you're joining, and also the data set becomes massive. And also what's cool here is because we have these nodes, which are entities, these are called canonical nodes. So they mean one thing. And if you do this properly, then we're going to have Sarah and the SChen and her email address linked into one node, because they describe the same entity, Sarah. And this, of course, will eliminate a lot of confusion, ambiguity in your responses, because you map them down to one single entity. problem with this, or no, not a problem. Yeah, it's a problem. We'll talk about that in a second. So the thing here is that what you need to do is you need to create ontologies. Ontologies, it's a big word. I looked it up this morning. So essentially it means it's a psychological practice where you try to categorize things. You make a map of things and you say, oh, this is a bird and this is a dog. And I don't know, you categorize items and try to put them in a schema, so to say. So if you want to build a graph database, what you need to do by hand, build one by hand, I mean, you need to first define what entities do we have. Cat, dog, Frodo, Pippin, person, whatever. All of that stuff needs to exist and need to talk about. You need to put it down, what you want. And also you need to look a little bit at how you want to manage your schema. So as I said, we have these meta entities like person, location. You need to figure out what these meta entities are, how they relate, how they can be. So it's a lot of work you need to put into that. And also, of course, the relations you're going to have, they are not necessarily bidirectional. So for example, a person can work on a project, but a project cannot work on a person. So you need to define rules on what are allowed connections between nodes. So there needs to be limitations on that. And then to make things a little bit more complicated, there's also taxonomies, which are hierarchical trees of things. So for example, a software engineer is a person, so there's more person than engineers, and there's there's more engineers than software engineers normally, so it's a category, it's a tree, and also this needs to be expressed in order to define a cool graph database for your use case. So the biggest problem rising out of that is that if you know where to implement this in your company, and you wander around and you say, hey, dear shipping department, can we sit down on a table and please talk about what you guys do and what the things you have and how they relate with each other and are there constraints, etc. And you do this a couple of times, then I'm fairly sure that the management will come around and pretty quickly ask us, what the hell is it you guys are doing there? Because it's very abstract, right? It's like, you're shaping some things and what the hell is this? So it's sort of hard getting the time to build a cool graph database. And of course, also departments get split, departments get merged, so you need to update the database quite a lot. Sometimes you need to review these changes really carefully because they can affect your whole graph if you slice one thing out here and put it somewhere else. So that's a thing. And of course, if you don't do that, the database will become out of date. And as you query it, you get rubbish results because it's outdated. So this is very time consuming. And this is why I think in the end, all these graph databases have not picked up properly yet, because they are very intensive to maintain. So you need to put a lot of effort into them. But we have LLMs now, which is great, because LLMs are very good at understanding stuff and are very good at reading text, and they're actually pretty clever about what they see in that text. So what people are doing now these days is they take a book, they feed it into an LLM and tell the LLM, hey, dear LLM, please look at the text and figure out what are the entities and what are these entities doing to another entity. So this is usually called a triplet. So it's a node, a relation, and another node. So this is how the LLM will give you output. So you feed it a passage, and then it's going to say, hey, Sarah, let project N. This is a triplet you have here. And obviously, that's the thing you stuff into your graph database. This is how you will generate the graph from a text that the LLM read. Going back to Lord of the Rings and leaving the project world, so what I did here is I have a section from Lord of the Rings, and I fed it into the LLM, and the outcome of the whole thing is this. I mean, you saw it before, but this is basically what fed this. So the LLM was able to figure out all the nodes, all the entities, and the connections between them, and this is all from this section. So this is what it came out of. Thinking about it, if you have Lord of the Rings, which is 1,200 something pages, the graph will be very, very large and probably quite tricky to understand. So this is where it gets complicated, because obviously it's a complex system, and the graph expressing all the interactions that you will find in these books is going to be tricky. So it's not easy to navigate. But for the graph database, it's not a problem. It's more for humans to grasp what's going on there. All right, cool. So we got Lord of the Rings in a graph database. What do we do with this now? Because in the end, this is a talk about RAG, so we want to get the data out of the system again and feed it into our LLM so it can talk about that. Simplest case, we can do this. So how this now works is I have a user query. All the data is in the graph database already. I forgot to mention that. So we take the user query up here, and we say, hey, take the LLM, use the user query, turn it into a triplet. And so the triplet probably is going to be something like Gollum is called name. It could be a possible triplet. You create an embedding with an embedding model with the triplet, and then you use the vector for the query to find all the nodes that are similar to the query. So in that example, I guess the nodes that it will find are Gollum-related nodes, because Gollum is also there embedded. So it's going to pull out a node, which is going to be our starting point. And then from that starting point, we're going to load the starting point, and then we simply follow all the edges of that node and load the neighbors, and take the response we get, feed it into the answering LLM, and then let the LLM answer on this. It works. Funny thing is, this works actually quite nice. The issue, of course, with this is that you get a lot of noise. So for example, if you do this and you load the Gandalf node, which probably has thousands of edges on it because the guy interacts with basically everybody in the book and is there a lot of times. So you would pull in a lot of neighbors of Gandalf, which are probably not related to the answer. So they are just too much. So you would load the context with pointless information. And the next approach to this whole thing is that you find the starting node, again, the same as before, and then you load all the edges of the starting node, and then you take these edges and you feed them to an LLM and say, hey, look, LLM, I got these edges, which ones should I follow? Right? So the LLM is going to say, yeah, since we're interested in names, perhaps you should follow the edges that have some name relation, and not every edge that you find. And yeah, you do that and feed it back, and then you get only the nodes that the LLM thought are mention worthy. Ignore number 5, please. Just notice this is a mistake. It doesn't repeat. In this case, it just does this once, follows the edges, gets the nodes, returns it. This is a mistake. Where this is coming from is this one here. This is like the most advanced use case that you can do with this sort of approach, is that you use chain of thought reasoning, where you still load the node, you load the edges, have the LLM look at the edges, and then load the nodes that the LLM should think. But then what happens is you give the result to the LLM and say, look, LLM, this is what we have. This was the user query. Do you really think this is answering the question? And then the LLM might think, perhaps it's not enough. Perhaps I should follow to the next node and load that data. Or perhaps I should start again because this is all rubbish and this doesn't answer the question at all. So we have this cycle in here, so you can see this with this error. So we go through getting the nodes and checking if they make any sense or not with an LLM until that LLM is happy. We get the results, and then we pass it out again to our answering LLM, which is a different LLM, by the way, to answer the question about how this works. So this is the most complex way that I ventured into. Of course, this takes much longer, right? Because the LLM iterates over it, so this can take a couple of seconds, while the first approach you get in, I don't know, 200 milliseconds or something. So this is much faster. All right, that's the theory. Let's see how it works, right? Or if it works. And oh no, sorry, forgot to mention this. Yes, there's more stuff. Just quickly go into that. What we did before is that we started off at one node and then ventured from that node out. There's also other approaches, which is called beam search, for example, where you start at 20 nodes and then venture out, and then you get the 20 results back, and then you look at which of the results is best, and then you use that. So it's like more in parallel. Obviously, it's quite resource intensive and also more tricky to implement, because also who decides what response is best. So this is going to take a lot of time. And then if you really want to dive into this, there's a lot of crazy stuff out there. So for example, one approach would be that the LLM can produce cipher, so these queries against the graph network itself. So it can really say, I have this node, I have that node. What's the shortest route from that node to this node? And then get the way and then extract all the nodes on the way and feed that. So these are possible algorithms. And as I said, this sort of graphs have been around for a while with these navigation systems. There's a lot of really crazy algorithms here that allow you the traversal of these graphs. Most cutting edge shit is this here, graph neural networks. So these are neural networks that exhibit traits of graph databases. It's very much in research, so I haven't seen anybody use this in production, but this is something that you find quite often. It might be that this is like the next big thing, because it sort of empowers neural networks to be more powerful, more seeing connections between items, and not so much just bluntly answering the next possible word that comes after a sentence. All right, here we are. This is what I wanted to say. How does it work? So going back to the initial question, what does this all mean for the formation of the ring, and what's Gandalf have to do with it? To recap, this is what it was. There's a birthday party. Gandalf wanders off, the ring stays with Frodo. Gandalf comes back, gets arrested, hobbits leave, and then they meet again in Rivendell to convince the elves that the ring must be destroyed. And this is the new answer. This is what we got back from using a GraphRAG system where we fed in the first book of The Lord of the Rings. And I'd say this is pretty good. I mean, this is not 100% accurate, so there's some stuff missing. So for example, what's missing here is that the hobbits leave early, so they leave while Gandalf is away, but okay, it's fine. But in essence, so especially the right part here, this is spot on. So the party triggers the story, and then Gandalf leaves, and then comes back, and they meet in Rivendell. So using the system, we were able to capture a really complicated question and answer it correctly where normal RAG systems would have failed. So I'd say this is pretty good. It's a cool result. And also given that this is like not a 4-year research project that I did, but I just used some libraries and sort of dove into the topic a bit more, this is pretty impressive. If you want to build something like this yourself, then I can say there's a couple of cool use cases that probably fit many companies you're working for here. So one is obviously enterprise knowledge management. So enterprises, a lot of people working on projects, knowing they are in a department, move from one department to the other. And a lot of this sort of implicit knowledge in a company is always lost. Does anybody know who worked on project X? I don't know. So it's very hard to sort of keep track of what's going on inside a company. And this is why such a system might really, really help building an enterprise knowledge management system where what's going on in your company is documented. And another thing where this would really shine is technical documentation. So for example, manuals. You have this, lawnmower, and there are spare parts for it, but this spare parts is only for this type of model, and the other one's for that type of model, and you cannot use this thing if you have something like that. So that's a fairly complex interconnections between things and possibilities, and this is also where this would shine, because you can really express what's compatible with this part, how do I need to do, what's the order of steps I need to do to replace that part. So this would really work, and then obviously also for software engineering, if you manage to leverage this thing with all the vibe coding, AI-assisted coding, etc., that's going on here, so that there's more of a train of thought and a chain of events happening in this, then also I think these systems could be greatly improved. All right, you get out of this is a lot of reduction in I don't know answers. So I pulled that figure from a paper I read the other day. I forgot to mention it here, sorry about that. Obviously, and you saw that in the demo here, is that the multi-hop accuracy is much, much better because, yeah, it's just meant to do these multi-hops as opposed to normal RAG, where it's just get the thing and live with it. And of course, also what's really cool about this is that it makes results more explainable. Because when you have a result and you trace the graph traversals that the LLM did in order to get to that result, you can actually see what's going on behind the scene and how did it get to that information. And this is also something in normal RAG. Basically, you have a vector and you get a chunk, and it's like, okay, however. And this is much more powerful in getting explainable AI results and obviously also reducing hallucinations because the data you fit in is more accurate. So some tips and tricks as sort of on my way out I want to give you if you want to build something like that. It's actually not so tricky. When you want to start, first thing is don't do it with your whole database. Try some small subset of the data so it doesn't take forever to build the graph. And then also, this is something that I cannot stress enough, have an evaluation data set. So you need to know if you're improving or you're getting worse. So what this means is out of your, 1,000 demo data sets, create queries, create expected responses, and then you measure how well does my system answer the queries. Accuracy, precision, all these sort of boring machine learning terms. This is where this comes to shine, because when you've done this with your normal RAG, you can test your GraphRAG and see, has it improved, is it better? For the graph database, I just go with Neo4j. It's a pretty cool system, and it comes with a lot of free tooling, and it's quite easy to use. I've used ArangoDB in the past, which is fairly cool. So I built a graph system for About You, was it 12 years ago, because they wanted to be a social platform at some point where you could like people and follow people, and then you would want to see who follows this guy and then who follows that guy. So this is what we used Arango for. It's also quite nice. It's also still around, but never really got big, I guess. If you want to do this, then set up the extraction. So you use the LLMs to get the triplets. You build the graph, or if you're lazy, you can just jump start the two first steps and use something like Zep or Cogni. It's these logos, you're going to find them if you search for them, because these are frameworks that come preloaded with a lot of stuff that basically ingests the documents, builds the graph, and also has an API that you can query the graph database. So for playing around, these tools are pretty cool, especially Cogni is also quite flexible in terms of changing how you want to index it. So I can recommend giving it a shot, because you get quite a while, you walk the road for quite a while using these tools before you hit their boundaries, obviously. Number 5, this is important, I think. Make it look nice. People are behavior driven. So if you give this to your test audience and it looks shit, then they will not like it. And they will not trust the results. It's like that. If it looks crappy, then they're like, yeah, okay, this is cool, but no, probably not. No, don't want to use that. So do the effort, build a nice UI, build a nice interface, make it snappy, make it fast, so people are going to like it. And people, if like it, they're going to start using it, and then it's going to get traction. And then it's not going to go into the basement and die there, but it's going to be part of your company, and it's going to be a cool tool that you build that helps people do their job better. So think about the interface, it's important. And obviously, if you already have an existing RAG system, battle test it. What's better here? For what use cases should I use this? For what should I use that? So this is where you can actually play around and then A/B test your results and see if you're really doing better or if you're just confusing people. All right, that's pretty much it. Think about this one. It's very big. I don't really know what it means, but you can change the company you're working for by thinking about bigger things of a bigger scope and try to implement something that makes everybody's life better and be cool at leveraging modern technologies. That's it. Thank you.